Hi, my name's Nigella Nakuna, and I am in Physics 2. I attended the public lecture about Einstein's cosmos and the quantum, and the presenter here was Professor Abhay Ashtekar. And so, moving into what I learned, it was kind of divided into four sections, and I did it in a chronological timeline. So, from the time of 1907 to about 1915, and then from around the period of 1930 to 1965, and then looking at 1965 forward, and finally the future state. And so, first, we looked at the discovery of general relativity. There was a lot here that I didn't know about. So, in 1907 to 1915, we had Einstein's revolution, which was basically the realization and the loss of the special relativity concept. And so basically this resolution was a new theory of space, time, and gravitation. And so in 1915, there was this discovery of general relativity that basically says that gravity is absorbed into the space and time continuum. And there was an unexplained feature of the Mercury orbit that was also explained in this new theory. So it was really novel for its time. And so when we talk about general relativity, we know that this is really a lot about geometry, and that space and time is no longer just an inert background or stage, and that the gravitational field was really encoded into this geometry of space and time because gravity was omnipresent and non-discriminating. And so matter really tells us how that space-time curves, and that space-time tells matter how to move. And geometry is intertwined within all of this. And so then we looked at the Big Bang, which was the birth of this space and time in the 1930s. And this was really around cosmology and the evolution of geometry. And so this really grew from Einstein's equations about space-time curvature and how that related to matter and stress energy. So basically, the issue in the beginning was that Einstein's equations applied to the general universe. So he was correct in kind of thinking through the Big Bang, and the Big Bang was correct in terms of how the universe began. And that was really where we started to form the Big Bang. He also related a lot of physics here, like I said, about cosmology and nucleosynthesis. And so he talked a lot about the cosmic microwave background, which basically said that when the Earth was 380,000 years old, the universe was extremely homogeneous, and it had a perfectly black core with a temperature 2.73 Kelvin as seen today. And so that really started to explain the Big Bang. So then we moved into this concept of inflation, which I was not really aware of. And we applied general relativity to cosmology, but ignored the fundamentals of quantum physics. But this was basically justified because they only really looked at the large-scale structure and ignored what happened in the early era before the universe was 380,000 years old. And so that's where this idea of inflation rose. And inflation is basically saying that after the Big Bang, soon after the Big Bang, the universe underwent this phase of rapid expansion. And when this phase occurred, the universe was completely homogeneous, except for the consistently present vacuum fluctuations, which couldn't be gotten rid of, even in the principle. And so that's really showing that inflation was the origin of the large-scale structure. But now we want to look at physics beyond what Einstein gave us. And so looking at the Big Bang theory to the Big Bounce theory. And so Big Bang really tells us the prediction of general relativity in a domain which is kind of still inapplicable, because we want to really look at singularities to physics beyond Einstein. And so we're really looking at quantum gravity and what difficulties there are now. So we have to be able to answer questions like, what are the atoms of geometry? How do these atoms fit together to give us a continuum? And can quantum gravity provide us with the equation that still hold beyond the Big Bang, where the continuum tears and classical physics stops. So that was all of the things I really didn't know. But in terms of the information I did know, I was aware, obviously, of the Big Bang, and also that there were a lot of twists and turns when figuring out how the universe began. And so in 1930, a lot of people were still debating whether Einstein's model was correct. And one of the famous quotes was that Eddington said was that, "Shall we put a little motion into Einstein's world of inert matter, or put a little matter into De Sitter's premium mobile?" And De Sitter was another individual who thought of different ways that the universe began. So there was this kind of dichotomy between what scientists thought at the time of how the universe began. And so there was a lot here that sparked my curiosity in the lecture, and a lot of it was this concept of inflation, which, like I said before, was the origin of the large-scale structure. But specifically within inflation, I was interested in the new cosmogenesis, which was the origin of the cosmic structure. And so it really talks about the quantum vacuum, and what the presenter talked about of quantum nothingness, which is a new structure of the creation of the universe. And I thought that that portion was really interesting, because there are a lot of problems that lie beyond inflation. Inflation still continues to assume that the space-time geometry is given by general relativity, and then it incorporates these small quantum corrections. But we do know that there's still a Big Bang with infinite matter density and curvature, and we know that the space-time ends, and inflationary physics also ends. So we need a more complete answer, and so they kind of moved into quantum gravity from there. But I thought this theory of inflation was really interesting. And so lastly, I did follow up with this topic of singularity, and did some research on my own into what it is. And singularity is basically, like it says on the slide, where general relativity suggests that just before the Big Bang, a point with zero volume and infinite density contained all the matter of the universe. And so basically the matter that enters this black hole also enters singularity as the volume reduces to zero and the density increases exponentially, or it doesn't stop. And so these singularities were first perceived as a result of Einstein's theory of relativity, and these resulted in the existence of black holes. And so the theory predicted that any star reaching beyond a certain point of mass would give off a gravitational force so intense that it would collapse. And so nothing would be capable of escaping its surface. And this is due to the fact that gravitational force would exceed the speed of light in a vacuum. And so I thought this concept of singularity was also very interesting.